Hello friends, today we will discuss how to implement a PI controller in discrete time domain and the integrator windup effect, and we will discuss one scheme for anti-windup. The transfer function of a PI controller is given by, so for example, if we have an error signal, we will have one proportional part which is nothing but kp times error, and this part is added with the integral part, that is ki 1 by s times the error, and the addition of these two component, proportional and integral, is PI controller output. Let us consider the output of the integral part is y int. So we can write y int is equal to ki integral of e dt plus its initial condition. Therefore, the output of the PI controller y pi is equal to proportional part kp into et plus ki integral of dt plus y int 0. To implement the PI controller as a discrete time system, we have to first discretize the integral part of that. For that, we have to sample the error signal first. So let us say we have the error signal like this. So we have to discretize this signal first. So we have to sample it at regular interval. So let us consider this is the nth sample of error signal, and this is en-1, this is n-1th sample of the error signal. So the integrator output will be the area under this curve plus the previous value of the integrator output. So we can write it like this: y integrator and sample is nothing but ts by 2 en plus en minus 1, and we have to multiply this gain ki, which is the gain of the integral part of the controller, plus the value of the integrator output from the previous sample. And this output we can add to the proportional part of the PI controller to get the total output. So y pi n is equal to kp times en plus y int. So this is the way we can discretize the PI controller. Typically, the output of the PI controller is applied to an actuator. So the output of the actuator goes to a plant whose output needs to be controlled. So this is error. Now if we have an actuator that gets saturated, that can give some undesirable effect. Or there can be another condition. Let's say we want the output of the actuator to be saturated. For example, we are running a DC machine. Let's say the output of the actuator is the current which is being fed to the DC machine, and we don't want the current to be more than the rated value of the current of the DC machine. So we have to limit the output of the actuator. Now let's assume that the actuator is such that the output is equal to input. So we can say that y pi is equal to I. So we can do this block diagram in this way. So for the modeling purpose, we have assumed that the gain of the actuator is 1. So in this case, the output of the PI controller has to be limited. Now if we want the output of the PI controller to be limited, how to implement this limiter? Let us say the output of the PI controller has a saturation block, which means we have a positive limit and a negative limit. So the output of this block cannot be greater than positive limit, or it cannot be less than the negative limit. If the input to this block is between these two limits, the output will be equal to input. So let us focus on this system. So we have an integrator and a saturation block. And let's say the output of integrator is y1 and the output in saturation block is y2, and the input here is E, error signal. Now let's assume that this is our error signal. So what is y1? Y1 will be integration of this error signal. We can plot y1 like this. And let us say this is the level of positive saturation limit. So the output y2 will be this. So basically what is happening, even though the output of the saturation block is limited, so the y2 is limited to its limit, but the output of the integrator, that is y1, that is keep on integrating. Now after some time, let us say the error has gone negative. So what will happen to y1? Y1 will start decreasing. However, it is still greater than the saturation limit. So the output of saturation block, that is y2, will remain constant. And the output y2 will remain at this level until y1 goes below the maximum limit. So at this condition, y2 will follow y1 like this. After some time, let's say the error has become positive again, y1 will start increasing, y2 will follow y1 up to this point. After that, it will limit again, but the output of the integrator will keep on integrating. So this problem of integrating, even though the output of the saturation block is limited, is called windup, integrator windup. So a way to get rid of this problem is to stop integrating as soon as the output of the saturation block hits its maximum or minimum limit. So how can we implement that? Typically we implement the integrator in a digital controller. To stop the integration, we can do the following. So we have an error signal and we have a proportional part and integral part. So we put a limit on the integral part as well as a limit on the output of the total PI controller. Let us say this is YA and this is YPI, and this signal is YInt and this signal is YP. So to implement the integral part with the limit, we have to check what is the previous value of the integral output. So YInt n minus 1, let us say it is equal to P plus, which is the maximum limit of the actuator output, and the area under this curve for this sample is greater than 0. If these two conditions are true, then the output of integrator should be equal to P plus. If the first condition is not true, then we have to check whether the previous sample is equal to P minus and the area under the curve for this sample is less than 0. Then we can make output of the integrator for this sample equal to the negative limit. If these two conditions are not true, then we can say the output of the integrator is equal to previous value plus area under the curve in this sample. Then we can add this part by int n with the output of the proportional part to get YPI, the output of the PI controller. Now it may happen even though the output of the integral is less than P plus, but YP is positive and the addition of these two is greater than P plus. That is the positive limit of the actuator. So we have to check if YPI is greater than P plus, then we can say YA equal to P plus. If YPI is less than P minus, then we can say YA is equal to P minus. Otherwise, YA is equal to YPI. So this is the overall algorithm to implement the PI controller with anti-windup. Thank you.